Chapter 3 is on the topic of functions, and the first section, 3.1, is about function notation, also the definition of function. First, though, I want to start with a simpler definition, which is a relation. A relation is a set of ordered pairs. And that can be very specific, as in the first example that we'll look at. It can be, I don't mean less specific, but a lot more points, for example, would be included on a whole circle in the xy plane. All those points, you could call that a relation. Here, I'm going to look at a set that's easier to write down. The set of 1, 2, 2, 4, 3, 6, and 4, 8. So those are 4 ordered pairs. You could think of them as 4 points in the plane. You could plot those on an XY plane. Graph paper would make that easier. Now, I'm going to extend this definition a little bit further to include the domain. I'll get more specific about what that is, but it's the first numbers. In this case, the domain is the 1, 2, 3, and 4, all of the first coordinates in these 4 coordinate pairs. And then the range is all of the second coordinates, 2, 4, 6, and 8. 2, 4, 6, and 8. Now, it's no big deal that 2 is in the domain and also in the range. 4 also, it doesn't really mean much. We're going to just, for relations, we don't have to go much farther than this. But the domain values are what we're going to call inputs. And this will become clearer as we go. The reason for this will become clearer as we go. And the range values are going to be called outputs. So the inputs for this function are the 1, 2, 3, and 4. And the outputs are 2, 4, 6, and 8. Next, we're going to look at a specific type of relation that we'll look at in much greater detail. This is going to be the main character for the rest of this chapter and pretty much for the rest of the course. A function is a relation for which each input has exactly 1 output. Another way to say that is that an input doesn't have more than 1 output. It has 1 output. 1 output. To look at some conceptual pictures of this before, we'll look back at some ordered pairs, versions of functions and non-functions to get some, see what they are and aren't. But before we get to that, let's look at the map picture of a function, which is to have a domain and a range, written as these abstract blobs that it doesn't matter what they're shaped like. I don't want to give any impression that they mean anything, but the domain is the set of inputs. So I'm going to put my inputs in here. Let's follow the book's example. P, Q, and R are the three inputs that I'm going to have in this example. And M and N are the outputs. And the function itself tells me that the input P corresponds to the output M. The input Q corresponds to the output N. And the input R corresponds also to the output N. Now, let's look at this in light of the definition. Each input has exactly one output. Now here's an output that has two different inputs. That's fine. It's still a function. So I'm going to continue with a couple more examples that'll show what a function is and what a function isn't in terms of these blobs. So first, let's look at this one where I have the inputs P and Q and R and the outputs X and Y and Z. And let's just keep it simple. Each one of these goes to one of those. And this is a function. Not much different than the one I did before, a little bit different, but what I want to use this for is to contrast it with, if I have inputs just P and Q and outputs X and Y and Z, where the output of P is X. The output of P is X. And the output of Q is Y and Z. And that's the whole point of this one. Here I've got one input corresponding to two outputs. And that's a relation, but it's not a function for exactly this reason. So I'm going to say not a function. And this is kind of how we're going to start looking at functions and examining their properties by contrasting and deciding which relations, these are all relations, all three of these, are functions. Only the first two are functions. This third one is not a function, so I've labeled it like that. I'd like to do another example of function, not a function, using the lists of ordered pairs like we looked at for relations at the very beginning. So let's look at, for an example, which relation or relations are functions. Or is if there's no less than one. Anyway, first, for part A, let's look at the relation 1, 3, 1, 4, 2, 5. So the domain here, the inputs, are 1, also a 1, and 2. So just 1 and 2. The range consists of 3, 4, and 5. That's not what we're being asked, but that's important to this. Now I'm going to write. Well, is this a function? input one has outputs, that's the problem, it's plural, outputs 3 and 4. So, not a function. And that's my answer to that part of the problem. This isn't a function because this single input, it's the same number, corresponds to two different outputs. That's exactly what a function is not. It's a relation. It's a set of ordered pairs, but it's not a function. As opposed to, let me just barely change this one above. 1, 3, 2, 4, and 3, 5. Now this one has a different domain. It's got the domain elements 1, 2, and 3. It does have the same range, 3, 4, and 5, but the important thing about it for us, and what makes it a function, is that each input, 1, 2, and 3, has a single output. Now you can spot the difference quickly if you just look at this list and see that two of them have the same first coordinate, the same input, different outputs. But this list, there's no repeats in the first coordinate. They're all different. So none of them has more than one output. And this is a function. So these are small functions, I would say. There's only 3 points in each of these functions, but they still serve a point. Well, I called it a function. That's not right. There's still a point in looking at them. So next we're going to look at some function notation that'll help us extend the idea of functions to graphs and be able to determine if a graph is a function. Next we're going to look at the function notation, way to write down functions in an efficient, compact way. And I'll just start by writing down the expression like this, f of x. It looks like I'm multiplying x, the number x in parentheses, by this, probably another number f, but it's not. F is for function, and that's the name of the function. If we have other functions, we might call them f and g and h. If there's more meaning to it, we might use something like p of x for the profit from building x robots or whatever you're selling. Or t of x, which is could be the temperature on a particular day numbered by x. So anyway, f of x is the most common one we'll use, f for function, and then of x. X is the input. And it comes from the domain, remember? Input values for a function are in the domain. The domain is the set of all the input values. Well, the output, you could call it f, but we're going to use another variable. Y equals f of x. Y will be our output. This is the same guy here. F of x, the input x, yields the output y. And f is the name of the function. So that's what the basics of what the terminology looks like. I'm going to write out another phrase here. Y as a function of x. And there's that phrase again, of x. F of x. Y is a function of x if for a set of x values, the domain, the f, the function of those x values gives me the y values, the output values, in the range. So the range, again, is the set of all the output values. The domain is the set of all the input values. And the function is the relation, it's a special kind of relation, or the correspondence between the two sets. Next, we're going to look at an example of how to use this function notation and what it really means in terms of algebraic expressions. So what I've got here is that we're going to complete the table for this function where I'm given this information. I'm supposed to use the x values, or the input values of 3, 1, 0, and -2. That's 4 different input values. It may be 4 different output values, but as long as each of these only has 1 output value, it's still a function. The function we're going to use is f of x equals 2x plus 1, and the table I'm making is an xy table. Now these y values, though, those are the f of x values that correspond to these 4 x values. So first, and this is how the notation is used, what I'm going to look at, I'm going to draw this off to the side, and then this will be where I'll put all my results. But I'm going to write f of 3. So f of x is 2x plus 1. F of 3 is 2, that's 2 times x, 2 times 3 plus 1. And that is 2 times 3 is 6 plus 1 is 7. And that's my f of 3, my y value that corresponds to the x value of 3. Let's do that again with the others. F of 1 is 2 times 1 plus 1, right? 2 times the x value plus 1, that's 2 times 1 is 2, plus 1 is 3, and that's the y value that corresponds to the x value of 1. Next, f of 0 is 2 times 0 plus 1, which 2 times 0 is 0, so it's just 0 plus 1 or 1. And that's my y value, that, or my output value that corresponds to the input value, or x value of 0. And then finally, f of -2. This is a little bit different just because I have to put some grouping symbols so it doesn't look like 2 minus 2. It's not 2 minus 2, it's 2 times -2, which is -4, and -4 plus 1 is -3, so that's my final output value. Of -3. So in short, f of 3 is 7, f of 1 is 3, f of 0 is 1, and f of -2 is -3. I've got this summarized in my table here, and you can see that these are ordered xy pairs. I could plot these. On a graph, and the shape would be a line, which you might have guessed from this. This is y equals 2x plus 1. That's the slope-intercept form of the line, which is the graph of this function. In that last example, we already did some of this, but I wanted to give a name to it. It's called evaluating functions. And in that last example, we had one function with 4 different input values. That means we evaluated the same function 4 times. We've already done this. But evaluate, look at the root of the word. It's value, and we're finding function values. At first, anyway, you'll be given input values. Later on, you'll have to come up with your own by experience and just being reasonable about it. But you've got to have some experience before that. So I'm going to do some function evaluating from example 6 on page 165. And we're given the function, the instructions are to evaluate. We're given the function f of x equals x squared plus 3x plus minus 4 at the following 3 values. First, and we'll do these sequentially. So for part A, we're going to use the value 2. Now, that's an input value. So what I mean by that is x equals 2. That's an x value. And to evaluate it, we're going to plug the number 2 into the function, f of 2. That's exactly what we want to find. So I'm going to replace the x variable in the formula for the function with the number 2. So f of x is x squared plus 3x minus 4. F of 2 is 2 squared plus 3 times 2 minus 4. And that is 4 plus 6 minus 4, which is 6. So that's the value of the function at x equals 2, or the value of the function for x equals 2. The next one we'll look at is part B, and they give us the value, the input value, A. Not part A, but the letter representing a number, that's a variable. The letter A. In other words, x equals A. And in this one, what I want to find is f of A. I'm going to do the same thing I did before, where I swapped out the x in the formula for the number 2. Except this time, I'm swapping out the x, the letter x, for another letter. A squared plus 3a minus 4. And that's it. Because I don't know what number the letter A represents. So my final answer here is another algebraic expression. So for part C of this example, we're using the same function, but we're going to use the input value of a plus h. So it's an algebraic expression. What I mean by that is we're going to find the value of f of a plus h. So f of x is x squared plus 3x plus minus 4. F of a plus h is a plus h squared plus 3a plus h minus 4. So I just did exactly the same thing I did last time. Instead of a number or a single variable, I have a variable expression. And I replaced x with that variable expression. Now I need to simplify this, but it's still going to have variables in it. watch out for this. This is not a squared plus h squared, and you know this. I have to, rhymes with toil, foil. So this is a plus h times a plus h. We can work on the rest of the expression also in this step. 3 times a plus h is 3a plus 3h. And then minus 4 comes along for the ride. I can't believe I said that. So in the next step, I'll do the FOIL here. So the first, a squared, outers, AH, inners HA, which is the same thing, AH and HA are equal. So I'm actually going to combine those two like terms in the next step. And then plus h squared for the last. So first outers, inners, lasts, plus 3a plus 3h minus 4. Sorry, it's getting kind of scrunched at the side, but it's that part's the same as the step before. There's no like terms. I can't simplify it any further. In fact, let me back up a little bit so it's not so cramped. A squared plus 2ah plus h squared plus 3a plus 3h minus 4, and that is as good as we can do with this because we don't know what the values of a and h are. And there are no like terms that I can combine. I've got an a squared term and an a term, but those aren't like terms. I've got an ah term here and an a term and an h term, but they're not like terms because they don't have all the same variables. And we're going to omit part D of this example. Let's continue with example 7 from page 166. This isn't a completely new process, but there's a little bit more notation here. For example, the problem says given the function h of p equals p squared plus 2p, that's a function h and an input variable p. Evaluate h of 4. So we've got new letters, but we're doing the same thing. What we need to find is h of 4, and I'm going to write my formula here with 4 in place of p. So it's going to be 4 squared plus 2. 2p means 2 times p, that's 2 times 4 in this case. And that's 16 plus 8, which is 24. So that's one more example of evaluating. The next thing we're going to do is solve function equations, which is kind of the opposite. Here, we're given the input value. In the next activity, we're going to be given the output value and have to find the input value that it came from. So this example, example 8 from page 166 is about solving functions. And I usually don't call it that, I just say solve, but for this problem, given the function h of p equals p squared plus 2p, the same function we used for the last example. This time, solve h of p equals 3. Now the information I've given here, aside from the function, is not an input value or a p value, but the value of h of p. That's, you can think of that as like a y value, and that, but p is the x value, and the y value is the whole function value, the h of p. Here we've got different letters, but the principle is the same. And what I'm going to do is, h of p, that's p squared plus 2p. Well, it says here h of p is equal to 3. So I'm just going to write p squared plus 2p is equal to 3. And you might be able to see that, why that is a little bit better that they're both on the board. H of P is this, H of P is this. So if it's equal to this and it's equal to this, then those things must be equal to each other. And that's something we can solve. This is an equation in one variable. It's not linear, so we can't just move things around and get the variable isolated. Can't do that. This is quadratic, so I need to subtract 3 from both sides to get p squared plus 2p minus 3 equals 0. Quadratic equation in standard form. Then I'm going to factor this, and I can do this one by the trial and error method because the leading coefficient is 1, so this is going to be p and p. That negative sign tells me that these two need to be opposites. The factors of 3 that add up to, oh, well, we could do the negative 3 tree here. Negative 1 and 3, negative, let's say positive 1 and negative 3. The ones that add up to positive 2, that's those. So I want the minus 1 and the plus 3. However, you could even do the full-blown AC method. It's just more than you need here. And now I can use zero factor property to split that into 2 linear equations, both equal to 0, or both factors equal to 0, and solve those individually. P equals negative 3, P equals 1, and those are the 2 p-values that yield an h of p value of 3. Now let's take a moment to appreciate that this is a function. This isn't an input value with 2 different output values. In that case, it wouldn't be a function. This is 2 different input values that have the same output value, which is fine. It's a subtle difference, but it is the difference between being a function and not.